So now, because actually this is the title of all what I explained, that it is topological connection, and what actually I mentioned a little bit only some connection of character which I presented with link invariants, but real topology, or not real, but it is some topology we had not. So, the structure of subject, how it exists now, it has the following parts, that if we have vertex operator algebras, then in some cases, and not in general at all, but if we have vertex operator algebra, then vertex operator algebra produce invariants of three-dimensional manifolds, or even more or less than that. This I don't know how to say. That vertex operator algebra produce what physicists and mathematicians maybe now are calling three-dimensional topological field theory. And also it is no, at least such a kind of story is known long ago, but such mathematical construction exists for 25 years, maybe more than that, but still a lot of open questions about this. And but other part of story is slightly more modern, and this is the statement that if you have a manifold, in known case, if you take four-dimensional manifold, then using four-dimensional manifold you can construct some vertex operator algebra, or no, it depends. So this construction is not exist or definitely in mathematical level, and probably even on a physical level it does not exist, but at least the fact that in some sense it is possible to do, it is no doubt that it is correct. And the point is that if somebody gives you four-dimensional manifold, that you can construct many vertex operator algebra, maybe many vertex operator algebra depending in parameters. And character of this vertex operator algebra, they are invariant of this, and they are connected with or sometimes even coincide with what is calling Waffe-Witten invariance of four-dimensional manifold. And so this second part of construction, and it does not matter that we can go here and then go to this. And no, probably yes, but right now it's too much. No, I will discuss and maybe present some statement about this first, but this part of story connected with instanton counting, and I will see maybe near the end what in principle we have here. But at least let me say something about that. So here are invariant of three-dimensional manifolds, and here also, as a part of this business, we have invariants of knots and links. So first step which we have here, it is following. So if we have a vertex operator algebra with some conditions, so it can be what people call a rational vertex operator algebra, or at least algebra which satisfies some finiteness condition. Anyway, it is a class of vertex operator algebra where such kind of story is working. So in this case, first of all, what we can do, if somebody gives you a Riemann surface, then you can construct some vector space, and this is vector space depending in Riemann surface, and and such kind of thing is topological by nature. So maybe it uses some additional structure, but in principle it is Riemann surface, some topological object of genus G, and we can correspond to this vector space. And if it is possible to do in many cases, but if we want good topological application, this space has to be finite dimensional. And name of this space, there are several names. Sometimes it is calling conformal blocks, or if from Atiyah and Siegel times, so it's 30 years ago, it is calling like modular functor. No, actually, it is some sort of cohomology, but it has the following property, at least, that cohomology, it has to be functorial, and in this case, we cannot expect something like this. But what is true? If we take a Riemann surface, and if we consider the group of diffeomorphisms, this group is not connected, and if we factorize group of all diffeomorphisms up to connected component of 1, then it gives us rather big group, which is calling Teichmüller group. And it can be understood, and it is a group of topological transformation of E times E, which are defined up to deformation. So Teichmüller group is acting here, and to be a little bit more precise, in all known constructions, this HE is a projective representation of Teichmüller group. Anyway, point is that vertex operator algebra give us possibility to construct this and establish many properties, and in particular the action of the Müller group is there, but it is not all. Many other properties there are. And about the construction, that if we return to the initial of all this theory, then in Siegel and in Atiyah it was the following construction, and it started with that. If we fix some group G and construct depending in G, suppose it is SL2 hat, for example, and if we have Riemann surface, in order to make this, first of all, we have to fix complex structure. And in principle, construction depends on complex structure, but not much. So if we deform complex structure, then we deform also this modular functor, and usually it formulated that we have some connection on the modular space of complex structure, and construction which is usually formulated is following. Well, if you have this group, then you consider the modular space of SL2 bundles. No, if you have modular space of some kind of algebraic object, even in SL2 bundles, you have some algebraic geometry problem just to define it. And even if you define, you will have a lot of problem how to work out with it. Anyway, suppose we overcome this problem, and then we determine the modular space of SL2 bundles on E. No, actually it is something which we can compactify, so it is compact rational manifold, and I skip all details about the construction, but it is something. And we also have here some line bundle which is calling determinant bundle, and then we can take this bundle power k, where k is calling level from the point of SL2, then calculate or trying to find out the section of this bundle, and this is a starting point of all such constructions. Yes, and actually we have a family of spaces depending in this k has to be non-negative integer, and so this is it. And in all construction, almost all construction, especially of construction of such kind of modular functor, the action of the Müller group there is completely non-evident. Yes, and so, as I said, vertex operator algebra gives you such kind of construction. Let me, no, because I discussed so much construction of semi-infinite spaces, semi-infinite construction of representations of vertex operator algebra. Now let me and I even in one of my lecture formulated some kind of construction which give you modular functor, and let me say now not this but similar construction. And now first of all it will be now first of all about construction. Let us take E and let us fix some line, two-dimensional bundle mu on E. No, in principle we can take any, but suppose that this mu is ample, so at least I want that zero homology of this two-dimensional is has dimension n, where no, n has to be big enough. Yes, but suppose right now that it is just big, it is n-dimensional space, and one-dimensional cohomology of mu, it will be zero. No, it is usual if this number is big, then one-dimensional cohomology is zero. Then my construction of modular functor, which will not be precisely this, but it is related to this. It is in some sense close, and this I say a few words later. What is this? But now let us do the following. So I have my E, I have two-dimensional bundle, and I can consider the projectivization of it. So it means that here each fiber is C2, but I can consider corresponding CP1 number of lines. And then it gives me what? As a result, it gives me something which is usually calling linear surface. What does it mean? It is natural correspondence that because for linear surface, what is this? Point of this is this A, which belongs to E, and line L, which belong to a fiber of mu in the point A. Therefore, I get some surface S and the map to E, and fiber in each point, it is this L. Yes, and also this is more or less evident from the elementary algebraic geometry that I can take on S, I have bundle mu, not on S. So I have line bundle maybe nu. So what is this? S is this, it is lines, and here I have line bundle mu such that H0 of mu just isomorphic to H0 of mu. So it is just tautological line bundle here. If I have this, now I can introduce my construction, and this construction is looks simple, only the point which is complicated why it is related with my business. Yes, and so I will construct sequence of spaces. For k equal 1, I do the following. So this dimension is equal n. Yeah, yes, and I can take s times s times s n times. Here I have line bundle, which is nu times nu times nu times and so on times nu. No, it is just outer, what's the name, tensor product of line bundle here, 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 and here. And for k equal 1, I want to consider a very simple space, which is just space of sections of this, let us denote it by n nu. But this space surely is tensor product, n's tensor product of this space, but I'm interested in skew symmetric part. Now, skew symmetric part, it is close to what I call determinant bundle, and to what people are saying like this. At least in this case, I get one-dimensional space, and it will be my modular functor for k equal 1. Now, right now, it is not very interesting, but next step, it will be k equal 2. In k equal 2 case, I have nu square, just considering again the nth tensor power. It will be line bundle on s times s times s. Here is n times. And now I want to take symmetric space of symmetric sections, but with additional property that such a symmetric section of this, they have 0 on the diagonals. Now, it means that I'm interested in symmetric sections of this, say f, it is section, such that f of S1 and so on, Sn is 0. It is symmetric, and if S1 equal S2, on such kind of diagonal. Now, the dimension of space, of this space, surely will be bigger, and at least it will not be so trivial. And in generic case, if k is something, what you are doing, you take s times s times s, and times you take this tensor product n, nu power k, and then what you are doing. So, well, there is 0 on the diagonal, but it is also not so trivial, because S run on two-dimensional manifolds. So it is condition of dimension 2. And in general, we have to take such kind of things and consider symmetric sections. If K is odd, skew symmetric if K is even, symmetric, is odd, symmetric with K is even, and next extra condition is 0. So it means that, again, my function f(1) Sn, it is 0 if S1 equal S2, but degree of 0 is equal K. Now, for example, if K equal 2, they are symmetric, and then because functions are symmetric and they're 0, that it means that degree of 0 is equal to. For symmetric function, it cannot be degree 1, and in general, it is like that.
The degree of at least 2 or exactly 2?
No, it has to be. It has to be vector space. So therefore, degree of 0 is 2 or more than that. Surely it is also.
That degree is 4. Is it allowed or not?
Allowed. If 3, if possible, also yes, and so on. It just a statement that it is 0 in this case S1 equals S2, but order of 0 we do not know. Just some 0. Anyway, I want. So this is pure algebraic geometry construction with semi-infinite business. It appears by the following way that I will say it because semi-infinite business was important for me, but before let me say the following. So standard construction which I had, it was, which I mentioned, it was that we have a model space of SL2 bundles on a curve, and then we have psi power k. Yes, and for example, that in this SL2 head construction, if you have E and if k equal 1, then it is well-known fact that in this case, the corresponding modular functor can be constructed by a simple way. And this simple way is following. Let us take E and let us take Jacobian of this E. And on this Jacobian we have theta divisor. And theta divisor, it is some standard divisor of codimension 1 as any divisor. And so here we have line bundle, say rho, line bundle, which is corresponding to this theta divisor, and section of this theta divisor is standard theta function. Yes. And no, it's okay, but we can take square of this rho it is also a line bundle on a curve, but number of sections of this bundle will be equal to power g, where g is genus of this curve. Yes, and first of all, according to the standard way of calculation of modular functor using Verlinda rule and so on, we get this number. But in this case, we get the same number, realizing this as a space of sections of determinant bundle. No, and from the point of view of modular space, it appears naturally because Jacobian, this manifold is complicated. I mean, all bundles, two-dimensional bundles, mu. But sum of such kind of bundles is the sum of two linear bundles, mu1 plus mu2. And such kind of things surely related with Jacobian, and it labeled by mu1. Therefore, in some sense, it is not completely precise, but almost. Jacobian is subset, submanifold of this modular space, and we can take the determinant, the bundle which is restricted to this Jacobian, and for k equal 1, it is isomorphism. Yes, and what is important? So this is the space of theta functions, and because this is a space of theta function, on this space of theta function acting as usual the Heisenberg group. And in the case of a curve, what we have to do, we have to take E, we can take H1 E over Z over 2Z. It will be finite group, but because we have product on homology, we have skew symmetric form on this group with value in Z2, with value in two-dimensional homology. Therefore, we can construct corresponding Heisenberg algebra. And the fact is that this Heisenberg, the fact is that space of theta function is irreducible representation of this Heisenberg algebra. And no, actually, it is k equal 1. If k is bigger, then it is, no, we cannot realize modular functor in terms of Jacobian by such simple way. It is not possible. But still, what is possible to see that on the standard definition of modular functor, we have action of a Heisenberg group. Yes, and and relationship with my construction. In this construction, again, I skip details, but for example, for k equal 1. For k equal 1 in my construction, I have one-dimensional space. And here we have space dimension 2 power j. And actually the vector one-dimensional is what? I can take inside this Heisenberg maximal isotropic subgroup and considering invariants. With respect to this, it will be one-dimensional, and it gives me that. If I make the same or similar story for bigger k, it will be away from this to that. Yes, and only a few words about semi-infinite interpretation of this construction. It is possible to say by the following. Now, first, let us take C2. Let us consider C2 times C ZZ inverse. First of all, what we have here is representation of GL2 times C Z inverse, and this is Lie algebra, and corresponding group also is acting here. So suppose this space will be something, say V. Then I can construct a space of semi-infinite forms, just taking the direct sum I had such construction in some of my lectures, just this. And I even explained how to localize this algebra to a point. I recall that I have this space, I put this space in a point, and then calculate co-invariants with respect to something, and it gives me, in this case, one-dimensional space. And this one-dimensional space, it was just up to duality. It is what I have for k equal 1 here. And if you try to know, well, what is going on. So in this case, I have semi-infinite forms, they are living here. And construction, as I said, here we have the action of something which is living outside, and I take co-invariants. And this co-invariance is one-dimensional space, but then if I go to a dual description, it gives me just, it can be, to dual space, it can be identified with skew-symmetric sections, what I have here, and even more than that, I can change the n, I can become n bigger, and change the bundle surely a little bit, such that number of sections becomes the same. And this top part, the determinant, will be canonically the same. And it is possible also formulate by the following way, a little bit more precisely, again very short. So in this space I have external vectors, and I can take some external vector and take subspace from this external vector which generate by action of this V. It is something what appear in a different business in all of my talks, and then I have this space and factorize it up to what is acting here, and then go to a dual space, and it gives me just that. So this is how it is going, and if I go to the next step is following. Well, I said I want to go from k equal 1 to k equal 2. So, well, I have semi-infinite plus, no, let me also skip this, v, but I mean the whole things. And I want to consider two copies. I can take other copy of this. But maybe it will be y1 and it may be y2. Yes, and according to this notation, we can say that on this space it is acting C2 depending in Z. Now I write down the action of these skew-symmetric operators, which it is just product, and this is generating function of this. Yes, and let me put 1 here, it means that they're acting here. Here we have the action of C2, 2. Z, it is acting here, and on the tensor product it is acting such product. And so what does it mean? It means that it will be 4-dimensional space depending in Z. And each component is such quadratic combination of fermions here and fermions here. And inside this, we have C3 depending in Z, because in C2 times C2 we can look and find this component, C3Z. Yes, and if you have such operators which are acting here, then we can look to this by the following. We have from these operators A plus Z, A0 Z, and A minus Z. And who are they? Here we have two components, plus Z and minus Z. Here I have also two components. And when I calculate product, for example, A plus is psi plus from here times psi plus from here, and so on. So on the tensor product I have such operators, and it is not so complicated to calculate the relations. And these relations appear in my talks, but not maybe in this concrete situation. But first of all, this guy is the sum of two fermions, and as I said, from that we can see that A plus Z square is 0. Such kind of story appeared. Then I can take, so what is this? It is psi plus Z1 times psi minus Z2 plus, no, because it is product of 2, so it is this plus this. So I have to write down psi minus 1Z times psi plus Z. It is this, and as it is, it does not satisfy any relation like square of this is 0, but what is easy that A plus Z times A0 Z is 0. Yes, and next relation is A plus Z, A minus Z, maybe 2 here, plus A0 Z square is 0, and it will be one more that A0 Z times A minus Z is 0, and next one, the last one, A minus 1, Z square is 0. So such kind of relations we can easily get from this construction. And again, naively, what is this? Or maybe not naively. We have something like C3Z. Then I calculate the product of C3Z. Then C3 times C3. And in C3 we have 5-dimensional component. And this component is 0. This is what we get. Now the logic of this construction is going by the following way. Well, we get such kind of operators and relations using the explicit construction where they are quadratic combination of fermions. Well, fine. But in principle, my logic in this case was following. We can forget about explicit construction and just consider abelian algebra, A plus, A0, and A minus, all depending in Z, so their components, and we want them to satisfy this condition. And I explained that such kind of game we can play it in many situations, and in this case I take commutative algebra which satisfy such maybe not so complicated relations, and I can repeat my semi-infinite construction for such kind of relations. And no, it is possible surely to do just from relations, or easily, and actually because we have realization through fermions, this realization is good if you want to prove something about such construction, but statement is that this semi-infinite construction for such relation give me representations of some vertex operator algebra. Actually, by the same way as I did in other examples. And, well, and after that, I can do, I can take algebraic curve, I can put this semi-infinite space in the point and calculate coinvariants. And then go to a dual space and, well, this dual space is realized. No, this dual space I explained. This is space of matrix element of something or correlation functions. And here they interpret it as section of something. And these sections, from this point of view, these sections are, they have some zeros which are follows from this relation. And if you reinterpret it as I said here, then, no, well, it was what? S times S times S. Here I had bundle nu, and then I consider nu square. And now nu, so this is a linear surface, so it is a collection of this. If I restrict nu to each fiber, so it will be tautological bundle on CP1, and it has two sections. And these two sections give you two-dimensional bundle on E, because it is S to E. If I have nu square, and if I restrict it to each CP1, then it will be square of the tautological bundle. It has three sections. And these three sections gives me three-dimensional bundle over E. And after that, on the language of this three-dimensional bundle, we just see my relation that this section on S have 0 on the diagonal. On this language, it is just equivalent to these relations. Again, all details it is impossible to explain now, but at least it is not so complicated and it is handleable. And just messages are playing with this relation, calculate the modular functor, how vertex operator algebra business prescribe, and as a result I get construction like this. Yes, and about generalization. If you want to generalize it to SLN, it is not a big deal. It is possible. In general, by general for E8 we need some other construction. Such things does not working. Yes. Now. Let me make one comment, and it is related with what I said, but right now it is just some like curious coincidence. So in this case, constructions, what I'm talking is very similar, and it is going on by the following way. Let us take C2. Yes, and let us consider the following. Let me take polynomial rings in two variables, and I want to consider let me fix some number R. So what is this? It is element of this, it is functions in x1 and so on xr, where each xi belongs to C2, and because of this, it has to be skew symmetric. Now, some people who deal with Gilbert's scheme point of a plane can recognize what is this. Namely, if I have C2 and if I fix number R, we have Gilbert schema of R's points. So it means it is some algebraic manifold. I recall that this HR is what? Element of HR is just ideal which belong to this, with condition that C dimension of Cx1, x2 over J is equal to R. So this is standard definition of HR. And then what are people saying? That on HR we have also so-called tautological bundle, because we have what people call Precesi bundle. It is what? That if I take ideal, then ideal determine this space. It is R-dimensional space. And so it is Procesi bundle and it is R-dimensional, but I can take R exterior power of this bundle, and so it gives me some line bundle. No, I had notation rho, but suppose it, instead of notation, no, why not? Let us use notation O1 for that bundle. It is linear bundle, and you can ask about space of sections. Space of sections of this bundle is just this. Yes, and the next things that we can ask O2 is just square of this equation, what we can say about sections. And the natural conjecture, it is not, if you know this, then formulate the natural conjecture is not so complicated, because in principle, section of this, section of this, section of this, and so on, they form the algebra. So if I have two sections of this, taking a product, I have to take section of this. And if I know that they are skew-symmetric things, I can take one skew-symmetric and take product to other skew-symmetric, and as a result I get symmetric things. It will be f x1, x2, and so on, xr. But now it is symmetric, but because it is product of two skew-symmetric, that it has 0 on the diagonal. And similarly, if you take product of 3, you go here, you get symmetric object which has 0 on the diagonal of degree 3, and so on. Yes, and it is not so easy to prove, and actually this is one of famous theorem of Hyman, that actually this space of such symmetric function, for example, with 0 on the diagonal, is it's just space of section of this. And similar story there. And anyway, by this way, I can construct something which is usually calling a Riesz algebra or something like that. I can take space of section this plus this plus this, and so on, which are, suppose I know they can be described by this way, and with evident product, and it can be understood as that Gilbert scheme in principle can be determined by this way. It is very simple algebraic construction. We get some graded algebra. The fact that it is component infinite dimensional, it produces some problem, but no, not very serious. We can take the projective spectrum of this, and it can be one of possible of definition of Gilbert scheme. And you see that because of some, it is, no, actually it is some puzzle for me till now, but it's some explanation that here the construction is going just along the same way. But the difference is that here it was C2, but here it was linear surface. But up to this, it is precisely the same story. Yes. No. Gilbert's scheme is very important in this instanton counting and so on. The problem only that if you want to generalize it to, for example, SL3 case, then logic is the same, but S replacing by not linear surface, but something three-dimensional, or such with a map to S, and fiber is CP2. But formulation is just the same, and construction is the same, yes, but it does not matter, maybe it has some, no, the fact that Gilbert's scheme is something like that, it gives at least me some inspiration. In three-dimensional case, Gilbert's scheme cannot help much because nothing is known. No, something is known, but okay. Maybe now a few words about this semi-infinite constructions and corresponding representation, semi-infinite construction for vertex operator algebra, but let me restrict just to no what I discussed maybe yesterday. Also, it was SL2 had case, and the logic was following: I can fix some key, and in SL2 I have generators EZ, HZ, and FZ, and in order to make semi-infinite construction, I can restrict myself only by E. For in representation of level K, it is EZ K plus 1 is 0, it is standard relation, but then using only this, I can construct semi-infinite space and then construct all direct limit, semi-infinite space. I can calculate co-invariants and so on. And it gives me some kind of semi-infinite construction. Well, what we can do in a similar way in a case of, for example, SL3 hat. Yes, and there are several evident ways. One way is following. In SL3 we have Cartan and plus and then minus, and M plus is generated surely by E12Z, E23Z, and E13Z. Yes, and they are currents to the nilpotent algebra, and one way we can use it by the same way how we use E here. It is also possible, but to write monomial basis in a representation by this way, it is complicated. But we can try to play, no, complicated because this nilpotent algebra is too big. We can consider the smaller algebra, just yes, and but smaller algebra holds this algebra. It is just this, but smaller algebra we can take, for example, this and this, and it will be abelian algebra. And if you in these terms try to write down the relations SL3, it also has some level k. So this is 1, 2, and this is 1, 3, for example. So let us just skip this and let us denote this AZ and this is BC. Then if you have level k, then it is easy to write relations. So namely it is AZ alpha times BZ beta equals 0 if alpha plus beta equal k plus 1. No, it looks like generalization of what I said for SL2, but for two-component yes, and in this case we have also no, we can use this construct semi-infinite space and so on, but in this case because these relations are monomial and simple in this case, then we construct monomial base by the following way. I can draw the lattice and numerate them by 0, minus 1, 1, and here will be components of B, so it's B0, B minus 1, B1, and so on. And here it will be A0, A minus 1, A1, and so on. Yes, and again, the question is that according to my knowledge or my experience, what I had, I want to present you monomials which give me a basis in a representation by a similar way, and it is doing by the following. Let us first to draw such system of triangle. Yes, and in both directions. Yes, and so my configuration, no, let us draw this A and B configuration. What is this? It is a function on such lattice. So in each dot, here I have some function, it is f, depending on these vertices L. Yes, and configuration, it is just such function, but surely with some condition. And this condition is following, that as usual they are integer, that fL is bigger than 0, but such kind of condition in these terms saying us that fL1 plus fL2 plus fL3 is less than or equal than k if L1, L2, and L3 are vertices of any triangle which we have here. No, it will be such kind of relation, and we also, no, because it is semi-infinite construction, I want in this direction to have a sort of dense packet, and in this direction it is going to 0. And so we want to fix the type of tail, and after that, now for example, if k is 1, so how it is going? We can put, for example, cross here, then and I'm going in this direction. So in this case, this is forbidden, then I can put cross here. And it prohibits this, and this, but next one, it can be here. Yes, and next one will be here, and so on. We have a tail of such sort, and I think that in such special situation, I think we have three different tails, and they are in correspondence with three representation of SL3 hat. Yes, and even in this case, analyzing of tails is interesting because for bigger K, you recover all possibilities for integrable representation of level K. So they're in correspondence with weight of SL3, which belong to this cuts, or maybe not cuts, but the table of integrable representation. Yes, so it gives us such kind of story, but what is more interesting in the sense that much less studies, that you see that we describe integrable representation in terms of this algebra. But we can do the following. We can take not this algebra, but principal. Algebra, and principal algebra is what? It is E1 to Z plus E2 3Z. Maybe it will be now AZ, and E1 3Z is BZ. And so this is abelian algebra, and for example, if K equals 1, then A and B, they satisfy the following condition. BZ square is 0, yes, and AZ times BZ is also 0. No, this is, it looks the same as we had before, but the last condition is not like that. We have to take AZ and taking degree 4, I think, Z. Yes, and it is equal up to coefficient B prime Z square. Yes, and degree condition is correct, that A has degree 1 in different sense, and B has degree 2. And I claim that A and B, they satisfy such relations. And so these things is very, very also easy to check. And what I want to say for K equal 1, I know how to check it, and it is done. For bigger K, this is the question. But the statement is what? That, so here is B prime. I have commutative algebra generated by A and B. And then I want to, my game is always the same. A and B satisfy some relations. Then I construct semi-infinite space, and by the same way. So it is some subspaces, then I go, and get the whole space. And actually, no, if you are talking about basis because of such structure of relation, it is not so easy. But not so easy, it means in this sense that I do not know the answer. But at least the infinite type of construction, it is working and gives me representation of the whole algebra. Then let me continue a little bit. If I take this in SL2 hat, what I mentioned yesterday, what was it? I can take k equal 1, for example, and taking in this case we have two integrable representations. Standard notation is like this. And notation is mean here we have level, and here we have how generator h times 1 from this is acting on the highest weight vector. So it is this. And I can take as example this representation. And in this representation, on the very top, I have two-dimensional spaces, probably many people knows. Then I can take this vector, and this is what discussed yesterday. I can act by EZ. E is element from here to this vector. The first is E minus 2, then E minus 3, and so on. And here the statement is what? That I can take this representation, I take this vector, and I act to this vector by operators E minus 2, E minus 3, and so on. As a result, it gives me some subspace. Yes, and I even wrote the character of this subspace, and maybe it's not good to repeat it, but this character is a function on Z and Q. Q count this degree and Z count this degree, and corresponding character up to monomial coincide with the character of Virasoro algebra from the minimal model of 2.5. Yes, and also I explained that in semi-infinite language I have, and this is character of 2.5, and this is character of vacuum representation for 2.5. Yes, and after that I said that space of semi-infinite forms, it can be splitted by no, it was semi-infinite forms, well, and it was 0, and I explained have we here cross or not. Then my whole space decomposed by the following way. So this part corresponding to 2.5 minimal model, and the part which is living here corresponding to 3.5 minimal model. And so such kind of construction for Virasoro case, it is on the language of Virasoro algebra, saying the following. But I have no possibility to explain something in Virasoro, but I only want to say that Virasoro, it has some special representation, special kind of category of representation, which are labeled by such rational numbers. And 2,5, or it is calling usually Yang-Lee minimal modular, things like that, we have two irreducible representations. And in a case of 3,5, we have three irreducible representations. Yes, and the point is, if I take Virasoro 2,5, and I take Virasoro 3,5, and if I write down product this times this, plus product this times this, then is this correct? Maybe this times this also. I forget. No, maybe, but on this level it is not very important. But you get the representation, as a result, you get vertex operator algebra, which in Russian we call just urod. Urod is, in Japanese, it is what? It is urod in Japanese. No, because this algebra is close to this, but it is distorted. And how to, in English, urod is what?
An ugly person. ugly person. Ugly.
In Nihonga, ugly, how to say? Anyway, it is this, and from the point, no, and also no, again, from the point of view of semi-infinite construction, I can play with these things by which way? As I said, we have basis, which is labeled by a configuration, and in this case, this configuration stabilized to such tail, and then what was it? I took some point, actually 0, and I decomposed it according, have I something here or not? If I have not, it is product of two things. If I have, it is also product of two things, and corresponding characters here and here, they coincide with the characters. If I forget about z, characters of Virasoro, and so it will be this times this, or maybe this times this. Yes, and by this way, so it is combinatorial counterpart of this phenomena, and vertex operator algebra part of this phenomena. That I can take 2,5 theory times 3,5 theory and apply the construction which is calling extension. And by this way, I get this vertex operator which is calling urod, and this urod in charge of this combinatorial phenomena. Yes, and it is fine, and in the case if we go to a SL3 head case, then from the point of view of extension again, I can take k equal 1 and consider, so here I have Virasoro. In this case, I have to consider double algebra. No, we have Virasoro and we have generalizations. Such generalizations are in correspondence with simple Lie algebra and some other objects. But next, after Virasoro, which is W2 in this notation, we have W3. Minimal models for W3. They are labeled by also rational numbers, and we have to take 3, 7 times 4, 7 and combine them. And this is possible to show that taking product of them and making extension, I can get a character of SL3 head representation. And something like a combinatorial version of this, it can be formulated by the same simple way. At least I do not know. And as I said, there for SL3 I can use A and B, and from the point of view of configuration, I have a rather nice combinatorial structure, which is also like that. And surely this splitting ideology I can use for this configuration, just fix what I have here, for example, and it gives me also some interesting combinatorial formula. But unfortunately, unfortunately, I do not know, but at least part which we have here and part which we have here, they are not a character of some vertex operator algebra, or we need to change usual vertex operator algebra with such properties is impossible. They do not exist. But maybe it is possible to invent something, and it is a good question. But if you change maximal nilpotent this algebra to the principal abelian algebra, in this case, no doubt that it relates with this. From the point of view of the following is true. So you can take vacuum, maybe not vacuum, but I cannot be very precise, because if it is I want to get vacuum representation of something, I have to put 1 in some position, but no, I cannot be very exact in this moment, but well, it is a representation of level 1, and I have one vector on the top, and to this vector I can apply this E12z times plus E23z and E13z, and it gives me some subspace in this representation, and this subspace has the same character like W3 representation 3,7. And no, if somebody, no, I think that it is from, no, in this case it is possible to prove, but the proof which I know seems bad and too complicated. And it is some challenge to invent some way to check such kind of statements. Yes, but no, from this, what is natural to expect because of this, and what is this? I take this W3 algebra and take, say, vacuum representation, L. In this vacuum representation, Virasoro algebra is generated by operators which are usually denoted by Li. And W3 generated by sequence of Li also because in any vertex operator algebra we have Virasoro. But additionally we have generators as J. Yes, and after that, if we want to get something like this, we have to do the following. In W3 algebra, we can introduce filtration, just saying that Li has filtration 1 and this has filtration 2. And if we fix this, then because it is generator, then we can construct filtration on the whole algebra and then go to adjoint space, and after that it gives me representation of something. It will be commutative algebra in this case, and it has Q grading because W3 has, but additionally Z grading because of this and this. And to be honest, conjecturally in this case, but it's no doubt that what we get this way and what we have here is just the same. Yes, and no, it is like if so. It is too many things to check. I checked or know how to check many things, but probably not all. Yes, and now this is the situation, but only 20 minutes remain and 25. But let me say some words about four-dimensional about four-dimensional construction and the fact that for any four-dimensional manifold in principle we can correspond vertex operator algebra. It is physicists claim that this is true, and Gukov, Waffa, and some other, they initiate some activity in this direction, maybe let me just very, very briefly say why, in principle, such kind of things can be correct. Then, the interrelation of several kind of ideas, and one idea is following, that if we have C2 or then C2 maybe after some compactification you can take SL2, or better to say GL2. And considering what people call the instanton manifolds, and from the point of view, from mathematical point of view, it means that we have to consider the modular spaces of two-dimensional coherent sheaves on C2 without torsion. No, such kind of objects are something like bundles, but for C2 we have not big amount of bundles, surely. But torsion, it means that we can consider, it is not bundles necessarily, but coherent sheaves. So it means it is two-dimensional bundle, but we can consider subsheaf which equals 0 in some point, or belong to some sections belong to some line in some point, and so on. So such possibility we have. And such kind of manifold, it has some topological number, say something like D maybe. And if it is one-dimensional, it is just Gilbert's scheme, which I talked about. If it is two-dimensional, it is more complicated things. And by the way, for these more complicated things, it is also possible to write down coordinate ring and also say what is defined by this way. But now it is algebra geometric description. Well, or it can be described in the Kojima-like version using keywords, and it is different version of describing the same things. Anyway, we have collection of these Gilbert scheme-like things. Two, it means that it is related with yes, and after that we can take the direct sum of K-series of them, better to say. And E, it means this is it's good to take equivariant K-series, because here is group of GL2 is acting, or even Cartan subgroup in GL2, and we have to sum up in D. Then the statement is, so it means here what we are doing, we study some manifolds from topological point of view, and K-series is some topological characteristic of them. Then we can sum up such kind of things, and here C star time C star is acting well, and so we have two equivariance parameters Q1 and Q2. Then it is also Nakajima construction, even not Nakajima-like, but Nakajima construction. He studied this also, that on this space, some algebra is acting, and this space is representation of some algebra, and it is possible to say what is this. For us now important the following: if Q1, so this is algebra depending on these two parameters. If Q1 is Q2 simultaneously go to 1, that corresponding algebra degenerate to some vertex operator algebra. And therefore it is what was calling AGT conjecture, and now probably it is not conjecture but theorem, but still it is terminology is like this. It is conjecture, AGT conjecture, but this is like, no, first of all, from the point of view of usual common sense, it is strange because, well, we're playing with something which is very far from any vertex operator algebra and things like that, but we can find this. And in this case, what is the vertex operator algebra we get by this way? We in this inside this we can find some Heisenberg, such hi, h minus I is I, and it is also vertex operator algebra, and also we can find some Lj. And Lj give us Virasoro, and the algebra which we get here, it is like that. And if we change here 2 by 3, that the corresponding algebra will be hi, li, I mean 3 here and 3 here, and additionally it will be new generator ck. Altogether it will be W3, which just appeared there. Yes, and again, still it is many puzzles, but logically what is going on? C2 is, no, C2, no, we can, for this construction surely, we cannot forget about complex structure, but in principle we want it. So therefore, this we want to understand as R4, or even open disk. And in principle, we can think that such kind of construction can be done for open disk, but here we get parameters of W algebra for equivariant parameters, but in principle, it is not completely necessary. We can no, it means that either we do this, or we can forget about instanton at all and just say that for R4 you want correspond, скажем, to say Heisenberg plus Virasoro, and central charge of this Virasoro will be our free parameters. Yes, and next part of a story that if I have four-dimensional manifold, in principle I can take disks, glue this manifold by disk, and then trying to glue corresponding Virasoro to some vertex operator algebra. No, this is good plan, but as it is, till now it does not working, it has to work. But no mathematical or physical construction of such kind, but at least we expect something like this. And the construction which are actually known, they are all doing on a language of extension of vertex operator algebra. And maybe it is almost last what I want to say. Well, here we have a disk, but we can consider the situation when we have CP1 and which is lying inside some four-dimensional things or two-dimensional in complex sense, and we can consider, so here I consider point and small vicinity of this point. Here I have line and take vicinity of this line. And it is starting point of construction of gluing. The small vicinity is what? It is like that, a bundle, transversal cotangent bundle to that, then vicinity we can understand how that we can take CP1 and cut it by this way to two disks, and then all manifolds we can understand as two disks, D1 and D2, and then we glue them. And expected things, which is in good correspondence with all calculations and all physical desires, following that inside, in the vicinity of this point, I have one Virasoro. In the vicinity of this point, I have other Virasoro. And I can take the product of them and then make up the extension. And it gives me new vertex operator algebra, which is corresponding to this. This is such kind of ideology, and so there are some amount of examples of such constructions. And for example, the extension which I considered, it is very, very special case of such things. So I can take this Virasoro 2,5 theory, I can take here 3,5 theory, I can take a product and then make up extension. And extension, it is extension, and in my special case, such kind of extension give me vacuum or non-vacuum. No, this urod. Things are constructing by this way. Yes, and so what kind of comment here can be done? So from this point of view, we're playing such kind of game. This times this constructs the extension, and after that, we can identify with the known things, which is more or less like this in this case. Yes, and when I discussed this, my initial point was the semi-infinite type of construction of this representation where in some sense I see this splitting. Yes, but no, actually what is the real story behind this, it is very unclear, because, well, it means that if I worked out with this semi-infinite construction from topological point of view, what I did, I took this and cut it to two disks, and this is actually what I did. But what kind of relationship is here, and how to understand it, it is big question. And no, in principle, the construction which people like Serezha Gukov and maybe me also, we expect that if we have some kind of manifolds and what kind of checking of such construction can be? That we can take some manifolds and we can cut it to pieces by different ways, and then make up the gluing procedure and compare the results. In very restricted number of cases, it is possible to see that we get the same things. So this is what is the story, and no, I want to finish, and I have to finish some moment. Surely about this variant, it is very interesting, and probably, definitely I skip too much. And also a very interesting point is the relationship of three-dimensional business and four-dimensional business from the point of view of vertex operator algebra. So here it is easy to ask questions, there are a lot of. And it is also a very interesting point in this business. No, in principle, I have 5 minutes, but maybe